In semiconductor manufacturing, survival is typically measured in months. We are currently operating at the 1 nanometer scale, building architectures where silicon layers are only a few atoms thick, and a single chip is rapidly replaced by the next iteration. But there is an anomaly. Designed in 1971, the NE555 timer relies on bipolar transistors housed in a rudimentary 8-pin package. Over 50 years later, foundries still produce more than 1 billion of these timers annually. They are still being integrated into new washing machines, drones, and high-end analog synthesizers. This persistence against Moore's law suggests that the 555 is performing a task that miniaturization alone cannot optimize. To find out why, we have to look at the geometry of the silicon itself. Looking past the plastic casing reveals a design built on a single, unwavering mathematical ratio. The name itself reveals the mechanism. At the center sit 3 5-kilo-ohm resistors wired in series, forming a precise voltage divider. By splitting the incoming supply voltage into thirds, the chip creates stable markers at exactly 1/3 and 2/3 voltage. 2 internal comparators monitor the voltage. When the charge crosses those thresholds, they signal a flip-flop memory cell to change the chip's output. This mechanical simplicity provides a form of electrical armor. Where modern microprocessors fail at the slightest electrical ripple, the 555 handles massive voltage swings, operating from 4.5 up to 16 volts. That resilience was a direct response to the corporate environment at Signetics in 1970. At the time, Silicon Valley strategy favored packing as many functions as possible onto a single die, satisfying a demand for complex, multi-purpose integrated systems. Engineer Hans Camenzind argued for the opposite, a single-purpose, isolated timing tool. Working without corporate backing, Camenzind spent nearly a year developing the concept, physically cutting the circuit masks by hand using a razor. His breakthrough came through subtraction. He removed every feature that wasn't strictly necessary for timing until the entire logic gate fit into a single cheap 8-pin package. By refusing to overcomplicate the design, Camenzind created an industry standard that made precision timing logic a commodity for manufacturing. That internal geometry yields exactly 3 behavioral states in the real world. In astable mode, the chip acts as an oscillator, generating a continuous square wave clock. In monostable mode, it fires a single discrete pulse, creating a finite delay. Finally, in bistable mode, it operates as a memory latch, holding steady until externally triggered. From household appliances to the telemetry systems in deep space satellites, electronics still require these 3 behaviors to function. While we push towards sub-nanolayer limits to gain processing speed, the 555 remains unchanged. Every digital network still requires a foundational pulse to coordinate its operations, a pulse that sensitive, high-density chips often cannot generate reliably on their own. After 5 decades, the 555 has outlasted thousands of its successors. It reminds us that some designs aren't just stepping stones toward a smaller future. They're the destination.